We'll wait for a couple more minutes in case anyone else is joining, and we'll start at 6:10. Okay, so hello everyone. Welcome to the last class of this problem, last official class. So I'll just share my screen. So let others join. Uh, 1 second, there's like some construction going on. I'll just close my door and come back. So yes, so as I was saying, hi everyone. So we finally reached week 8 of our problem solving classes and also of your lectures of this new NPTEL course of nuclear astrophysics. So I hope that this has been a fruitful course for you all, and you have had, what I hope that it has met your expectations of what you wanted from this course. So, as I said before, this will not be the officially the last problem solving class, because we will be having one more session sometime this week, which is will be dedicated to some revising the course as a whole before you have your exam. So yeah, but this is the last, official kind of problem solving session that we have for this particular course. So yeah, let's just go into it. So I think you all know by now about, what these sessions are. I don't need to introduce it to you. Same we have been doing for the last 7 weeks. So yeah, in the final week of your lectures, you saw a lot of things. So we were kind of, these last two lectures of your course have been focused on more of nuclear physics and particularly more of experimental nuclear physics. So we kind of take a break from astronomy and come back to Earth, to the lab, to see how we exactly measure nuclear quantities and how we manipulate nuclear reactions in order to learn more about these underlying particles. And that is very important because we, as astronomers, we have, or astrophysicists, we have this kind of drawback when we compare to any other branch of physics, which is that we do not get to set up our own experiments, right? We only have access to one experiment, and that is the experiment which is running with us in it, which is basically the experiment of the universe. And we only have access to this one universe for now. So we kind of have to measure everything according to that. So it's nice to go back to, nuclear, more core nuclear physics, where we do have access to design experiments, and those findings can then be applied to the sort of reactions that we see in space. So that's something that I really like about astrophysics, and that really drew me to astrophysics in the first place, is that astrophysics by its very nature, or astronomy I should say, by its very nature, and even astrophysics is a very interdisciplinary subject. So you need physicists, you need engineers, you need biologists, chemists. You will find every sphere of science has a role in astronomy. And similarly, in astrophysics, you will find that nuclear physics is there, statistical mechanics is there, relativity is there. You have all the different spheres of physics which themselves play a role in astrophysics. So, yeah, so in these last 2 weeks, you have been kind of going more into the nuclear part of nuclear astrophysics. And that is, nice for me also, because as you know, I am an astronomer. These things are somewhat new to me as well. So through teaching this course, I have also been able to learn some of these things with you. So you learned about detectors, about various ways in which to measure the energy of nuclei. So there were direct methods, but that direct methods have various drawbacks, like you have to overcome the Coulomb repulsion, for instance, those kinds of things. So there are indirect methods where you can measure the energy and properties of nuclei by inferring them based on certain other properties. And then you also generally learned about kinematics of collisions particularly. And this is extremely important because this is how, the greatest or the largest, particle physics and nuclear physics experiments are set up. They're set up based on very simple principles like two billiard balls hitting together, but you just scale that up to high energies and high sort of scales. So one of the most important discoveries of probably our lifetimes that we saw in the last decade or so was the discovery of the Higgs boson. And that was basically a result of collisions at high energies, like what was done at CERN. So these are the different things that you have been seeing in your week 8 lecture. So as I said, I am not a nuclear physicist. That is a big caveat. I work in some nuclear physics, but I am not a nuclear physicist, and I'm definitely not a nuclear experimentalist. So my knowledge of these things are somewhat lacking. But what I have done today is I thought that I will focus on the one thing that I do know, which is about collisions and relativity. And I thought that since it's the final class, and I'm sure that you have covered all your, detectors and, scintillators and accelerators in your class, I wanted to kind of take a step back and, sort of motivate the idea of special relativity and relativistic collisions to you, because as relativity is something that is having a central role in physics, and definitely in astrophysics and nuclear astrophysics as well, because we deal with extremely relativistic particles. And we have spent, like, significant time in this lectures to look at quantum mechanics, which is the other big sort of giant of modern physics. So I think it's only fair that we close out by looking at a little bit of motivating a little bit of special relativity. So if you have already had exposure to this, this might be kind of basic to you. I'm sorry, but you stick around and we'll do the problems. But I thought it'd be nice to like close out by motivating some important results of special relativity, and looking at E is equal to mc squared more carefully. So yeah, so essentially this is what you were what I was talking about is collision. So you know that you have a particle, this is basically your generic nuclear reaction. For example, if this is a photon, then it's a gamma reaction and whatever, no, whatnot. So you have various kinds of properties depending on what is various kind of classification depending on what exactly x capital X small x capital Y small y are. And you have already learned the different classifications of these reactions. So here we take the generic reaction and we say that, okay, considering my nucleus is impinging on a target, then how do I get the final thing. And you know that here this is something called an elastic collision, and elastic collision is where momentum and energy is conserved. So here I have written the momentum conservation. You also know how to write the energy conservation, which is a scalar equation. But momentum conservation, of course, you have to consider the x and y components because momentum is a vector. So the directionality is important, and that's how you, by manipulating this set of equations, you can get expressions for vx, vy, theta, phi, everything. So you can get a complete description of the system. So this is a very simplistic view of what is actually happening. But this does not take into account a lot of things. And one of the important things that it doesn't take into account is that there is a cosmic speed limit. So, yeah, before we go to that, you also learned about cosmic speed limit, and we'll get to that. That is related to your special relativity. But yeah, before we get into that, you also saw that there is this kind of concepts of changing between frames when it comes to collisions. So you saw that although we perform experiments in the lab frame where maybe one particle is at rest, and here it's a photon that is hitting a proton and it is producing a pion and another proton. But again, you can think of this as x, y, and y like before. So if we have a generic reaction, you can think of it in terms of a generic reaction. But the point is that even though we perform our experiment in the lab, sometimes it's easier for us to change to something called the center of mass frame. So what is the center of mass frame? So essentially what happens is we are changing to the frame of the center of mass. Instead of observing from the lab where maybe your origin is somewhere here, you're here and you're observing the process, you imagine that you're observing the process stationary at the center of mass of the system. And the center of mass is that point where you would have done this in your class 12 or something. But center of mass is essentially the place where your masses and radii are scaled in such a way that you get a single point where the excuse me, if someone's unmuted, if you have a question, please ask. Otherwise, please mute. There's an echo. Okay, I'm going to mute you. If you have a question, you can unmute. But yeah, otherwise there's an echo, so it's kind of distracting. That's why I muted you. Okay. So as I was saying, the center of mass is essentially, so in extended body, please mute yourself. Yeah, thanks. Thank you. So yeah, in extended bodies, the center of mass is the point where you can apply Newton's laws essentially. The center of mass is, basically in a mass distribution, you can consider it to be equidistant from all the other masses in the system. So, for example, the Earth and the Sun is a two-body system, right? But because the Sun is so much massive than the Earth, the center of mass is basically very close to the Sun, and we can consider it to be just a motion of the Earth alone. So center of mass is very useful because in the center of mass frame, everything momentum is conserved. Momentum is basically zero before the collision. So you find that after the collision, the moment we don't have to consider the motion of the particles. So it makes it a little bit easier to do the analysis. So why do I bring this up? You have already seen all this, how to do this, and the exact mathematics which is required for this. But the reason that I brought up these two slides is to tell you that both of these contain very important things about physics. So one is, as I said, this picture lacks in something, which is exactly your speed of light, cosmic speed limit is not playing a role. And here we have used something very, very inherent and very fundamental to physics, which is that whether I'm in the lab frame or the center of mass frame, the physics processes I analyze are the same. So that's why I have the liberty to change from the lab frame to the center of mass frame, and back again after I do the analysis, I can change back to the lab frame. And that gives me the liberty. So this concept that physics laws are not depending on what frame you use is a very fundamental concept, and these are the pillars of special relativity. So let me just say that again because it's very important. Your laws of physics does not depend on your reference frame, because reference frame is drawn by us, right? We decide a reference frame. So I find usually that when students, when you take a math physics problem, and this is something that I had to learn over my somewhat many years of doing physics now, is that some physics problems are hard because they are physics, they're hard from a conceptual perspective. The physics is very involved, we cannot visualize the system, such things are there. But some physics problems are difficult because of the mathematics involved, right? So you should always be careful as to which part is the physics and which part is the mathematics, right? It might not directly affect you right now when you're when you're solving a problem for this exam, but when you're doing physics as a physicist, it and you're dealing with problems that maybe have not been solved before, it is important to keep in mind that whether I'm struggling with this problem, from a physics perspective, is it that my concepts, I'm not able to apply some concept here, or is it that the mathematics is too involved? This involves solving a differential equation of some higher order that I don't know how to solve yet. So those are the kinds of distinctions that you have to make. And the point is that the physical process does not depend on the mathematics you use to describe it, right? So I choose mathematics as a tool to represent whatever physical process is happening, which is this gamma ray hitting the proton, right? That does not depend on whether I'm observing the lab frame or the center of mass frame. The physics process should stay the same. And when we take that into account, we should have a way to convert between frames. So this is the essence of special relativity. And this is what I wanted to discuss today. It's the same thing as if you have a distance between 2 points, right? if you uh, if you measure it in centimeters or in inches, the answer, the numerical value you get might be different, right? You might get 2 inches, which is whatever in centimeters, it's like 5 centimeters, I guess, or roughly. So but because 2 and 5 are different, that does not mean that your distance itself is changing. It's simply the way that you describe it which is changing. So if you feel like this is a very simple concept or a very elementary concept to understand, please bear in mind that this is the backbone of one of the most celebrated discoveries, or celebrated kind of formulations of modern physics, which is relativity theory, both special and general. So the important thing to keep in mind is that the laws of physics are the same no matter what reference frame you're in. And to some extent, this is what we've been doing so far, right? We have been looking at things that are done on Earth, and we have been applying those same laws of physics to things which are far away, things in galaxies and galaxies away, light years away. We are applying the same laws of physics. So that is kind of where this can be motivated from. It could have been a universe where there is one set of laws on Earth and another set of laws in the heavens, and that's kind of how people thought, like very early on in the discovery of science. But we are lucky that we exist in a universe where the laws are somewhat, are the same throughout. And for that, we can be lazy and find out things on Earth and kind of extrapolate or interpolate and extend those to space. So yeah, so this is basically finding out what the minimum required energy is in the lab frame is not easy, because you have to account for the kinetic energy of the particles after the reaction. So you use, reaction products are standing still, which is center of mass frame. It's sometimes called the center of momentum frame in special relativity, but you don't have to be worried about that. So the center of mass or momentum frame is the frame in which the total momentum of all the particles adds up to zero. So essentially, it's the frame where, all the masses are equidistant, their momenta are zero, so you're kind of standing still. That's why it's useful to use that. So again, the reason why we're able to do this conversion is because the laws of physics are invariant in different frames. So with that, why do we need special relativity? So already we have spoken about quantum mechanics, right? So we found that Newton's laws were inadequate when we go to very small scales, which is, the scale of atoms and, protons, electrons. We found that, to describe the classical atom itself, we had to invoke something like quantum mechanics, and the simple classical mechanics did not do. Similarly, when we reach very high speeds, there also Newton's laws seem to break down, and there's a lot of weird things which happen. And to describe all this, we require special relativity. So special relativity is the more general theory which deals with things moving at very high energies or velocities. As you know, they are all related. So why is this important to us? Particularly because we are nuclear physicists. We deal with accelerators that, accelerate particles to extremely high energies. And we already kind of touched upon this when we talked about synchrotrons and cyclotrons. But for example, this is a picture of the LHC. I guess this is one of the experiments that's going on there. So, in super colliders such as the one in CERN, which is where the LHC, the Large Hadron Collider, sits, which is in Geneva, Switzerland. And also there's another accelerator experiment in USA, which is no longer active, I think, called Fermilab. You see that small particles like electrons and protons are accelerated to speeds near that of light and collided with each other, and these energies are high enough that exotic particles which we don't usually see can pop up. And this is exactly how the Higgs boson was discovered in 2012, if I'm not wrong. So the reason why this can be done is, of course, because of Einstein's very famous equation E is equal to mc squared, which I'm sure you all heard about even before what you knew what relativity was. So the point is that when I collide particles at extremely high energies, that energy can be converted to mass, and that can give me a new particle. And we have been using E is equal to mc squared all throughout this course, right? The whole reason why, there is a mass defect or nuclear reactions happen is because energy is converted to mass and vice versa. So relativity is very inherent to nuclear physics in general, and we have been using it even if we haven't called it by its name. So I thought in this last lecture, let's just motivate a little bit of relativity. So yeah, one very famous picture of that comes to mind, or special relativity. So special relativity is a lot like quantum mechanics, right? In the sense that it's very non-intuitive. So we are, kind of spoiled because we live in the, we our lives are in medium time scales. Like we live in time scales of years. We interact with things of the, length scales of meters and kilometers. We don't really go to extreme cases. Either we don't deal with very small masses, and or we don't deal with very high energies. And so we don't have very good intuition for very high energies or very small masses. So that's why quantum mechanics is not very intuitive to us. Similarly, relativity is also not very intuitive to us, because relativity really comes into picture when the velocity of an object reaches very close to the speed of light. And the speed of light, as you all know, is like 3 times 10 power 8 meters per second. So it's like 3 lakh kilometers per second, if I'm not wrong, or close to it. So because of that, we don't really have an idea of what happens at those velocities. We will never reach that. And at the velocities that we operate in, uh, Newton's laws are perfectly good approximation, right? And that's why we always start with learning Newton's laws and doing all those kinematic problems in that way, because that is exactly what we deal with on a daily basis. But of course, when we venture into the worlds of stars and atoms and nuclei, we have to start speaking their language, and that's where relativity plays an important role. So this is important, like, this is one of the many so-called paradoxes which comes in special relativity, which is the twin paradox. And this was kind of illustrated in Interstellar, which I'm sure you have all watched, where the father goes to space, and by the time he comes back, his daughter has become older than him. And people or the way people argue is that well, if he sees him as younger, then because everything is relative and all frames are valid, shouldn't he see him as younger as well, in the case that they both should appear younger than each other? So who's really younger? So the point is that these frames are not equivalent, because this person goes and comes back, so there is an acceleration involved. And the whole concept of which frames are equivalent and which frames are not is a very important question in relativity. So here when I say a frame, it means my reference frame in which I'm observing the event. So for example, these are two frames, right? Lab and center of momentum frame are two different frames. Similarly, I have two different frames. One is the frame of the twin who stays on Earth. One is the frame of the twin who goes to space. And the reason why, it's not a paradox is because the frames are not equivalent. One frame goes and then comes back. So there is an acceleration involved, whereas the other frame is not accelerating. So you can formally solve this problem using the mathematics of special relativity. But of course, that will go a little away from our course, but I highly encourage you. I have put like a nice blog post about it. If you are interested in this sort of thing, you can check it. And if you have some background in STR. So, yeah, so as I've been saying, there are only two postulates of special relativity, which is that one is the principle of relativity, which says that all the laws of physics are same in all inertial reference frames. And this makes sense to us. And this is why, again, I'm able to transfer between center of mass and the other frames and so on. So this is a very important principle. And I think, you would argue that we don't need a special name for this principle. We've kind of been implicitly using it, right? We use center of mass kind of arguments in Newtonian mechanics as well. So the point is that the more subtle point and the more sort of point that we are not used to comes from the fact that there is a cosmic speed limit, which is that the speed of light in vacuum is the same for all inertial reference frames, regardless of the motion of the observer or the source. And this kind of puts a correct speed limit on Newtonian mechanics. And as we approach the speed limit, things start looking weird. So the one of the consequences of this is that we don't have absolute time anymore. So Newtonian mechanics, there makes sense to, when, change from one frame to other, we don't really see the time changing, right? The time that elapses between two events does not change. Whereas, as you can see from this cartoon, time can pass differently for different observers depending on their motion. And this is a consequence of the fact that we need to keep the speed of light the same in all reference frames, right? So you can think of it like speed is distance by time. So when I change from one reference frame to another, if my distance is changing, then my time should also change in such a way that the speed of light remains a constant. So speed of light ensures that, there is always some weirdness in special relativity when it comes to length contraction and time dilation. So these are all things that you will learn in a special relativity course. Probably you've already learned this, and I'm again sorry if this is kind of elementary to people who are here, but I thought, in case someone doesn't know. So one of the things that happens now is that space and time mix with each other in a way that does not happen in Newtonian mechanics. And for this reason, we now deal with four-dimensional space-time instead of space or time separately. You can see that an event is now described by, of course, its position on the XYZ axis. Here is two frames, but also by what is time coordinated. So everything has four coordinates instead of three, as we expect in Newtonian mechanics. So as I said, not all reference frames are equivalent, even though I said that the laws of physics should hold in all reference frames. There is such a thing called an inertial reference frame. So an inertial reference frame is, are those where Newton's laws hold, right? And they are basically moving, they are non-accelerated frames. So they move with either constant velocity shifts with each other. And all inertial reference frames are equivalent. So when there's acceleration involved, you can describe it using special relativity, but you have to keep in mind that it's not necessarily always equivalent, right? So because the accelerated frame will produce its own effect. So it's similar to Newtonian mechanics in the sense that, for example, in Newtonian mechanics, when you go to a rotating frame, right, you see these new forces come up like centrifugal force, Coriolis force. These are not forces that are produced by any object as such, right? These are forces that arise because the frame itself is rotating. Like that, when a frame itself is accelerating, that can lead to further effects. So in that sense, there may be extra forces called fictitious forces that show up. So this is all very consistent with Newtonian mechanics. It's just we are formalizing it in a different way. So the point is that now we have a framework called special relativity, which states these two postulates, which seem very simple. But because of the speed of light constraint, we see that time and space kind of mix with each other. And philosophically, special relativity becomes very different when we compare with the regular Newtonian mechanics. So this is kind of a very nice chart I found while preparing the slides, which shows how different quantities, change when we take the speed approaches the speed of light. So give me a second. So again, as I said, you don't have to throw out Newtonian mechanics, right? Similar to how, apart from describing atoms and very, apart from where the wave nature becomes particularly important, we can pretend that there is no wave nature and apply Newtonian mechanics to ordinary objects. So the same way, we only need to care about special relativity in some sense when we approach the speed of light. So you can see how many effects that approaching speed of light has. There is of course length contraction, which is that moving objects seem to be shorter. There's also time dilation. These are things which have been observed, by the way, by experiments. And this increases the relativistic energy with an apparent increase in mass. We'll get to this. Affects momentum, and then you have a new energy momentum relationship. And of course, that affects the kinetic energy, the momentum of the photon, which we describe using PC. And there's something called four vectors. So we can't just deal with the normal vectors that we do in regular Newtonian mechanics. We have a whole new formalism, which is called. So again, as I said, we don't just deal with space now, we deal with space time, and these are described using four vectors. So you can see how many different quantities get affected by simply having two simple postulates of special relativity. Again, I'm just giving you a flavor, so I'm not going into any of these concepts in great detail. These are very well basic concepts and you can find them on your own. So this is basically the concept that I was talking about in the beginning, which is how to change between different frames. So you can see that we have two inertial frames S and S bar, and we know these are inertial frames because this is moving with a constant velocity with respect to this. So we are not really in an accelerated frame. So we have this Lorentz transformations which kind of relate the quantities in the primed frame with the quantities in the non-primed frame. And you can see that gamma here is called 1 by root over 1 minus v squared by c squared. And when gamma, you can see that when gamma is c, then this is not defined because nothing goes at c except light. And you can see how when as gamma gets smaller and smaller or bigger. Yeah, when gamma gets smaller, that indicates that we are in much more relativistic conditions as opposed to gamma bigger. So basically, when we approach a C, that's when we have relativity becoming important. So this is extra stuff for you again. I think some of you, if you have taken a special relativity course, this will be kind of known to you, which is that now because things are expressed in space time, we don't really deal with Euclidean space, which is a three-dimensional space, but we deal with four-dimensional space called Minkowski space. If you don't know what that means, don't worry about it. Point is that you can draw these world lines and you are restricted to this particular cone, future cone in your time, because that is where causality is consistent, and these lines are basically the speed of light. So all massive particles cannot move more faster than light, and information cannot be passed between objects faster than the speed of light. So don't worry that special relativity does not lead to any weird things like the cause happening before the effect. So cause happening after the effect. So causality is maintained, and that you can prove by looking at these kinds of space-time diagrams. So the point is that now we have what's important to us really is this energy momentum relationship, and that's kind of why I want to motivate this whole thing in the first place, because I'm sure that in your particular course you have seen already relativistic collisions, and how when we measure relativistic collisions we cannot just take the momentum to be mv, we have to take it to be gamma mv, because the as particles move at higher and higher speeds, the energy contribution from the rest mass energy also has to be taken into account, and the momentum can get weirded out. So I started this lecture by telling you that E is equal to mc squared, Einstein's famous equation. But because we're talking about special relativity, I wanted to tell you all that E is equal to mc squared is not really the full story. And sometimes you hear there is a way in which E equals to mc squared can be made to apply to all situations because of something called relativistic mass. So if you have taken a special relativity course, you might have heard this concept that particles gain more mass when they move faster and faster to the speed of light. But this is actually kind of an outdated notion, because right now how physics is done is you can express it in different ways. But the way to think about it is actually that the mass remains constant when you move closer to the speed of light. Is the momentum that increases, and that seems like an increase in the mass, but it's actually because of the relativistic energy momentum relationship. So this is a very short video that I can just play right now to show you the exact relationship.
But what you might not know is that E equals mc squared may be the most famous equation in the world. But what you might not know is that it isn't the whole story. It just describes objects.
So E is equal to mc squared is only for stationary objects,
the full equation,
right? So
E squared equals mc squared squared plus p times c squared, where p represents the momentum of the object in question. This might all seem a bit confusing, but in fact, you can draw it as a right triangle with sides E, mc squared, and p times c. And just use the Pythagorean theorem, a squared plus b squared equals c squared, to give you the equation. Also, from here, it's clear to see that for an object that isn't moving and thus doesn't have any momentum, and thus p is 0, we get back our good old friend E equals mc squared. On the other hand, if the particle in question is massless, like light, then mass is 0, and we get E equals p times c. This tells us that the energy of a massless particle, like a photon of light, is the same as its momentum, up to a factor of the speed of light. In fact, the closer the energy of something is to p times c, the closer that something is to behaving like light. I mean, look here, this tiny little bit of mass is hardly mass at all. Anyway, as an example, an object's velocity is equal to the speed of light times the ratio of the object's momentum to energy, or pc over e. If your momentum increases, p times c gets closer and closer to equaling your energy, so their ratio gets closer and closer to being 1, and your speed gets closer and closer to light speed. But because of that tiny little bit of mass, the momentum side of the triangle will always be a little bit smaller than the energy side. No matter how hard you try to increase your momentum, it never quite gets to the point where p times c equals your energy, and thus your velocity can never quite reach the speed of light, all because the hypotenuse of a right triangle is longer than its legs.
So the point is that massive particles can never move at the speed of light, no matter how hard you try, because the momentum keeps, even if you increase the momentum, the energy you require becomes at some point becomes infinite to reach the speed of light. So you can never speed up a massive particle to the speed of light. On the other hand, massless particles like photons always move only at the speed of light, because that is what special relativity dictates. So this is kind of how you think about it. Sometimes it's useful to approximate something that moves very close to the speed of light as moving at the speed of light. For example, neutrinos, which we spoke about in some early lectures, have very small masses, less than an electron, of the order of an electron volt or so. So because of that, it's basically okay to consider them moving as at the speed of light. But you should always keep in mind that that might be 99.999% of the speed of light. It will never actually be the speed of light. Similarly, in some problems, you will see that electrons can be thought of moving at the speed of light, and it might be like it's very close to speed of light. You can just consider it to be c. But I just wanted to show you this because one thing is that E is equal to mc squared is a very famous equation, but you should know that how the full equation actually looks. I also wanted to motivate that relativistic mass, sort of that concept is kind of outdated, and the way to think about it is that PC term kind of increasing. And the third thing is that, massive particles, which means particles that have mass, not very heavy particles. Massive particles always move at speeds which are less than light. But because we deal with approximations in physics, sometimes you can put them as basically moving at the speed of light, but you should be aware that that is not the full picture. Okay, so in this assignment also you will do one question where you kind of assume something is moving at the speed of light, but yeah, I just wanted you to know the caveat behind it. So here is a question that I have. I just thought that, because we spoke about, so my goal here, I don't think, you would have, if you've already seen special relativity, everything I said would not have been new to you. If by any chance you haven't taken a formal course on special relativity, this is a very beautiful subject. I would say that this guy, Minute Physics, he has a very nice series on special relativity, and you can find lots of resources online for learning about it. And I think it is a very cool and non-intuitive subject, and it's where all these, science fiction writers get their concepts for father being older than younger than his daughter and all that. So that the root of that is in this science. Okay, so this is a problem where a particle of mass m moving at a speed v is equal to 4c by 5c speed of light collides inelastically. So inelastic means that it's colliding and they are moving together, or they are stuck together or something like that. So they don't just collide and leave each other alone. Collides inelastically with similar particle at rest. What is the speed of the composite particle and what's the mass? So I chose this question because suppose I gave this to you, sorry, this question to you with no knowledge of special relativity, you would say that, well, it's very easy, right? You have 4c by 5, you have 0. I just do an addition of velocities, momentum conservation, and I will get some, 2c by 5 as the answer, right? It'll just be half of that, because that's how momentum conservation works. There are two similar particles and all that. There's 2c by 5 or something like that. I can't just do the math at the top of my head. So, but the point is that because relativity is concerned, you will see that the answer we get, because this is 4c by 5, 4c by 5 is 80% of the speed of light. So we are quite close to the speed of light. So we do need to apply relativity. So you can see how the solution is. I've just put the solution here. This is from a Feynman lectures problem. So you can see that there's a particle mass and there's another particle which they are calling R, which is, and the composite particle which forms from them both like sticking together is called C. So you can see that the momentum of the moving particle is not simply mv. It's mv scaled by 1 minus v squared by c squared. So already you can see that instead of 4 by 5 mc, we get 4 by 3 mc. So that's what I mean by, if I just simply did this in the Newtonian way, I would not have got the correct answer, right? So this is why I wanted to motivate why special relativity is important. And these are the kinds of things that you routinely see in your nuclear physics, right? You see particles moving at extremely high speeds and colliding with other relativistic particles. And if we were to simply apply the laws of Newtonian mechanics there, we would be wrong. So you can see that the square of the energy is mc squared plus p squared pc squared, mc squared the whole squared, pc squared the whole square. So this again you can remember based on the triangle method in the video. Particle at rest does not have PC, so we have only mc squared. So the composite particles has this, and then based on conservation of energy, we know that m plus r should give c. Of course, energy is still conserved when it comes to special relativity. It's just that we have to consider all the different components of energy. We can't just consider energy to be mv squared by 2, but there is a contribution from the relativistic aspects as well. So then, then after that, you just do some maths. So you can see that if I square this quantity, I'll get em squared plus er squared plus 2 er is ec squared. And I know all these quantities because of these expressions. From that, I can substitute. From that, I can do some more maths. And you can see that by doing all the maths, you get mc is actually 4 by root 3n. So even though two particles of the mass m have collided, the final mass is not 2m. It is something a little less than 2m. Right? So that's what I wanted to tell you, that quantum special relativity is important, because if we had just used normal relativity and we would have said the mass is invariant, doesn't matter, then we would have got the wrong answer. So here the answer is not that the mass changed because of moving faster. It's just that the energy contribution to the mass also matters, and that's why the mass appears to be different. So you can see the momentum of the can be calculated as well, and from that we get c by 2. So you can see that 4c by 5 plus 4c by 5 does not give us something like, which is higher than the speed of light. It always whatever value you put, you will always get something which is less than the speed of light. So this is about one problem, which is exactly a relativistic collision problem. So you can compare to the first slide, and you can see how the mass, even though we have conservation of momentum, how those expressions are slightly different because we have to include gamma in everything. And gamma is your sort of relativistic factor, right? This gamma 1 by root over 1 minus v squared by c squared. And yeah, this is another problem which I won't explain in detail. It's kind of the same thing. You can see a photon of energy 500 keV scattering from an electron at rest, and there are two angles. So they've given you that there's a gamma particle and an electron produced, and this electron, basically there's a scattering problem. So the photon loses some energy, the electron also starts moving, so the photon transfers some of its energy to the electron. So do you know what this process is called? This process has a name, and we had discussed this last class. Can you guys tell me what it's called? Where a
Compton.
photon, yes, Compton scattering. So this is a problem on Compton scattering, and you can see how, you can solve the system of equations. You can put this in and try it yourself and see how the answer comes out. So here you don't, again, you have to use momentum conservation in terms of the total energy. So in Compton scattering, we really did not, I don't know, did we? Yeah, we consider gamma photons to have speed of light, photons to have momentum like pc, right? And it's challenging to explain in Newtonian mechanics how a particle which does not have momentum, does not have mass like the photon, still has a value of momentum, because in Newtonian mechanics p is equal to mv and that's it. But because we know that in special relativity energy can also has two contributions, which is pc and also mc squared by to the power 4, we know that even though mc squared is 0, we still can have energy in terms of the photon can still have energy in terms of its momentum by e. So the momentum can be described in terms of the energy e by c. So to really understand how E is equal to PC comes, we do need special relativity. So this is just my way of, because as I said, I'm not a nuclear physicist. I'm sure that professor has made much better way of describing all the detectors and all the, nitty gritty of experimental nuclear physics to you. But what I can motivate to you is special relativity. So that's why I chose to, sort of give you a flavor of special relativity and the regimes in which it becomes important. So to scare you or to end it on the final note, uh, special relativity isn't the full picture, and there is something a little more advanced called general relativity, and there, you actually think of the curvature of space time and how gravity isn't really a force, but it is a manifestation of the space time curvature itself. And there's something called the famous Einstein equation, which I've shown here. The essence of general relativity is in this quote by John Wheeler, who is a very famous black hole physicist. He's actually the one who popularized the term black hole. He's the one who coined the term wormhole. So he's a very influential physicist, and he says space-time tells matter how to move, matter tells space-time how to curve. And I'll just leave it at that because GR is a beast in itself, and this is really not the forum to talk about it. But yeah, for more details, find a GR course near you and have fun with it. This involves way more mathematics than anything that we have done so far. So with that warning, I will leave you to it, and we can go back to doing our problems. So before we go to our, your regular week 8 content, which is solving problems about detectors and so on, I just want to remind you that this is not, okay, this is technically the last class, but we will have one more doubt clearing and, revision schedule class on Wednesday. So that will be at the same time 6 to 8, and during that session we'll actually have a full revision of topics. So I'll try to give you an overview of all the concepts, and it can be like a quick revision for you. If you guys have something from any of the weeks that you didn't understand or that you want to be explained again, please mail me with it so that I can accommodate that into the class, and that will be the final class. So try to, if you have something on your agenda, some agenda of yourself that you want to incorporate in that class, please mail me by by tomorrow, so that by Wednesday I can keep it in the slides. So yeah, please mail me sooner rather than later so I can actually incorporate it in the slides. And yeah, so in that class we'll have a general overview of all 8 weeks and all the topics, so that it'll be easier for you when you go to your exam. And yeah, we'll just have a this thing. Ma'am, can you explain about cross sections in next class? Yeah, yeah, sure. So by cross sections, you mean that yeah, I think we had one class, right, where it was like the relation between cross section and resonance and this not really resonance, the gamma peak and the gamma window and all that. I guess that concept. But yeah, I can generally touch upon all that also. Any other concepts also? Yeah, please, like, so this person has said about cross section. Similarly, if anyone else has any other agenda, please let me know, and we can kind of go through it together again so that it becomes a final revision for you. Okay, so I think we can move to the questions for today. Your technically our last set of questions. So yeah, the first question is here. As usual, please put your answers in the chat. I'll give you some time to solve the question. This is a thin target foil is kept in the line of a beam for irradiation. So you already have learnt about this kinds of experiments where there is a target and there's a beam line, and the beam line strikes the target, and as a result you can get you can study what are the nuclear reactions that happen and what are the consequences of that nuclear reaction. You can study the energies, cross sections, etc. So these are called beam line experiments. They happen in particle accelerators, for example. And here they have given you the current of the beam, and they have charged beam, and they have asked you to find what is the charge that is resulting after 1.5 hours. So I think this is not a very complicated question. I request you to put your answers in the chat. I am also monitoring the chat here. So okay, someone says A, others. I see one answer in the chat, A. Others, please answer as well. Okay, one more A. I'll give some time in case others are still solving. Time I will also check. Okay, someone says B. I'm waiting for some more answers before we go to the answer. Again, this problem solving session, the reason I conduct it like this is so that you actually go and solve the problems. And I hope that because for the last 8 weeks, you have been sincerely solving problems, studying for the exam becomes a little easier because you have the habit of solving problems. So yeah, please, like, make sure that, either during the session or after the session, that all the videos are available or the slides are available. All the slides have extra material that I've put links in all the slides so that you can go and explore also. So please, like, make use of these things so that, you might not need to go out and search for problems. You can always start with solving these problems and then, kind of use the other things. So, okay, I see two people say A, two people say B. Others, please, like, put your answers also in the chat. I I want to see what is the majority answer. I'll give you one more minute. This is not a very difficult question, but yeah, in case someone is still solving, I'll give you one more minute. Any other answers in the chat? I see two A's and two B's. I wanted to get us kind of a majority. So that's why I asked if anyone has any more answers. Okay, if not, we can go to the answer. Okay, thank you. So one person has said A. With that, the majority is correct. It is A. Others, please check your answer. So basically, this is a direct question. You know that charge is current into time, and that's what you have to use here. But of course, here the time is in hours. Coulomb is basically ampere times second. So you have to convert hours to second. So maybe that's where some of you went wrong. I don't know where exactly went wrong, but yeah, basically 1.5 hours into 60 for conversion to minutes into 60 for conversion to seconds. So basically 1.5 times 3600. So you get that quantity times 12 nanoampere. So this is 10 power minus 9. So when you do that, you will get 6.48 times 10 power minus 5. So people who have made mistake, please check and make sure that you understand how to do these questions. So it's a direct question. It's just based on current times time, which I think you know from your earlier physics, elementary physics as well. Okay, so this is the next question. Which of the following is an indirect method of cross-section measurement in nuclear astrophysics? So, as you saw in your course also, direct measurements is difficult for cross-section measurement. So, there are some indirect measurements. The point is which of these methods are the indirect methods. So, please go through. Please let me know. Yeah, I see one person says B. Others, okay, one person says D. Any other answers? I only see two people who have responded. I don't know if my wife. Let me just check. Okay, one more person says D. Yeah, okay, I see few people saying D now. Now I can the messages have gotten updated. One person says B. So yeah, the answer is actually B, all of the above. So the people who said B, you're not wrong. Trojan horse is an indirect method, but so are inelastic spectroscopy and spectroscopy of resonance. So the point is that direct methods have their own challenges, which you have discussed in the class. So these are the other methods. I think you already saw in detail about this Coulomb dissociation in the class. These are some other methods. So essentially here, instead of measuring the cross section by directly producing a reaction, you try to do the cross section measurement of a related reaction, and from that you can sort of translate whatever the cross section you measure to what is the reaction you're interested in. So as I said, I am not a nuclear physicist, so this stuff was new to me. So when I saw these three, I thought the Trojan horse sounded very intriguing, so I kind of looked into it a little bit more. So I think you're all familiar with this Trojan horse story, right? It's said that during the Trojan War, which happened between the Greek and Romans or something like that. So there was this, kind of smuggled their soldiers inside this huge wooden horse, which they acted like was a gift. So, through that wooden horse, the soldiers were inside and they came out and they attacked and they captured Troy. So that's how the Trojan horse comes. And the Trojan horse method is called that because you kind of sneak in a related reaction that is related to the expression that you want to study, and through that expression you learn what is the actual cross section you're interested in. So instead of studying x plus a going to c plus c, which is at some low energy and that has its own challenges, we then, instead of that, we go to some excited reaction which happens above the Coulomb barrier, so we don't have to worry about Coulomb repulsion or anything. And then we can then we are kind of using the wooden horse here is that related reaction, and then we can go back to the original reaction and kind of understand how that is related to this. So we kind of indirectly study the energy related by looking transferring to a different reaction, which is a three body relation, and from that learning how the initial reaction happens. So this is about the Trojan horse method. The other two are also kind of similar things. Inelastic spectroscopy happens in something called heavy ion collisions. Again, you bombard the ion with reaction with a lot of things, and then you form composite structures, and from that you can find resonance is also somewhat similar, where you go to resonance states and unbound states, and from that you can kind of measure what would be the cross section. So the point of indirect methods is to not study the reaction directly, but to kind of go to a regime where some of the problematic things like the Coulomb barrier are not an issue anymore, so that we can really study what the cross section is. So this is the next question. Which of the following factors is crucial for a radioactive ion to be considered suitable in beamline experiments? So yeah, please put your answers in the chat. Okay, I see someone has said C. Others also, please answer. Sorry, sorry, sorry. Any other answers? I only see one answer, C. Okay, one more person says C. Okay, one more person says C. Others? Okay. I see that. Okay. Okay, fine. So I say most of you are saying C, which is the correct answer. So here we can just go through the options one by one. So, obviously mass of the ion being higher than that of 56 Fe, ion 56 is not really a problem. Ion is traveling at speed of light, or nature of, obviously it depends on the nature of the radioactive ions, so this is wrong. So for us the stability matters, but it's not necessary that it should be a very heavy ion, right? The point is that the radioactive ion should be the half life should be larger than the transit time through the accelerating and transmitting sections of the accelerator, and this makes sense. Even, simply from a logical perspective, if the half life was not as large, then a good chunk of our radioactive ion in the beamline experiment would have decayed off before we even got a chance to accelerate and transmit into the actual experiment, right? So we need ions which are stable along the length scales that we consider. So that's why, even though it's a radioactive ion, its half life is very important. Half life is, I know you all know, half life is when it decays to half of its initial composition or initial amount, and that should be large enough that it does not decay before we get a chance to to perform the experiment itself. So it's a very logical question. Okay, so I keep saying that direct methods are difficult, and that's why we have this Trojan horse and other indirect methods. But what are the exact challenges that happen when we measure cross sections in nuclear astrophysics that requires these things? So please, like, put your answers in the chat. Okay, I see someone saying A. Someone says D. Okay, I see a couple of people saying D. Okay, good. You are all answering fast. I'll give one more minute in case someone else also wants to answer.
Hello, ma'am. Hello, ma'am.
Yeah. Hello.
Yes, ma'am. While doing this nuclear reactions, that is in experimental nuclear reactions, so we are aware of the radioactive sources. So this radioactive ions means how do they prepare these ions? I mean, because we are only familiar with these nuclei which are radioactive, right? Because then what does this ions mean that they are
Yeah. So
mentioning?
a nucleus is an ion, right? If you are going to remove an electron from it, nucleus is positively charged ion, right?
Yes.
So in that sense, they mean ions. Heavy ion collisions, they mean they use excited nuclei essentially. So if you want a charged beam, for example, you need to use positive ions. That's the kind of reason that they say radioactive ions. Is that okay?
So in the sense that they take these, if, for example, if it's 56 iron, they take the atom of 56 iron and make it an ion, atom, and then make it an ion by removing an electron, and then do the experiments.
Yeah, there must be some, yeah, if you need a charged ion of particles, then yeah, like for example, alpha particles. Alpha particles are positively charged helium nuclei, right? So when we perform experiments with the alpha particles, those are positive ions. So even though they are helium nuclei, they are positive ions also, because we have actually we don't consider the electrons, right? So that same way.
So basically, when you're talking about this radioactive, any sources that we are talking about, all are ions.
Yeah, so I think it depends, but like for example, in LHC, it's done with proton beams. So those are positively charged beams. So yeah, I think similarly, I don't know if neutral beams are used. I know gamma beams are used, for example, though those will be neutral. So you don't have to think about the charge. But if you're using positively charged beam, then it matters whether it's an ion or a electron kind of electron beam or an ion beam, right? So in that sense, that's why they use radioactive ions, is what I think.
Okay, ma'am. So in order to accelerate these charges, accelerate these, they have to have a charge, right? So that may be.
Yeah, exactly. You accelerate it through the electric field, right? So you have to have some sort of mechanism. Or like you have to use photons which are neutral, and that has to be produced by some other mechanism, and then you have to use a photon beam or something. But I think in these experiments, what we need is charged particles, because we are probing the nucleus. We don't really care about the electrons, right? So in that sense. So it's
Okay.
similar to alpha particle B.
Yeah.
Yeah. Okay. So I think this question you guys have answered, or let me just see. Yeah, I can see that a lot of people said D. So the answer is actually D. So all of these things contribute to the measurement of cross section. So of course, one thing is that the cross section is kind of low, and apart from that, we have a lot of contamination. So we have this cosmic rays, which are as I said, like there are very high energy rays which come from various astrophysical processes occurring in the universe. So last time we spoke about a few of these kinds of processes like Bremsstrahlung and Cherenkov. But yeah, there are lots of other radiation, synchrotron radiation, Compton scattering. All this is happening. All this produces photons and excited particles, and this all basically comes as cosmic rays. So we have to kind of that becomes a background. And another background is of course that the target and beam itself can contaminate your experiment when we want to exactly study something. So we have to be careful as to those things. So we have to remove all those backgrounds and then only study an experiment. And because it's already a very low cross section reaction, becomes challenging to kind of narrow down only that. Sometimes the background is larger than the signal, and that's a problem. So, this is the next question. Which of the following is not a component of time of flight experiment in nuclear physics? Please put your answers in the chat. So, as you know, time of flight experiment is when you measure the energy by how fast a neutron or any sort of particle takes to cover a certain distance. And based on that time, you can estimate the energy because energy, velocity, time, these are all related quantities. Okay, I see one person saying D. Okay, one person says C. Okay, I see someone else says D. Others, I'll give 2 more minutes in case someone is. Or actually, this is not requiring any solution. Please put your answers now itself. Okay. Okay, I see one more person has said D. So yeah, the answer is D. you don't really need pulses, right? What you need is like you need a time amplitude converter, which is what a TAC is, that allows you to measure the time, whatever time is measured to great precision, you can convert that to an amplitude. And then particle and gamma detectors are required so that you can distinguish between what are actually the neutrons and what are some secondary emission or something like that. So sometimes you give pulse thing, but that's not really necessary. Sometimes you use neutrons which are produced from other experiments, so that's why those three are the main thing. So the next question, this is a numerical question. So this is a nuclear experiment to calculate efficiency of sodium iodide or titanium iodide detectors for gamma rays. You use some sort of cylindrical detector. It has this following uh, dimension. The detector is kept at some particular distance from the gamma ray source, which is cesium 137. And from that, I want you to calculate the solid angle subtended by the source on the face of the detector. So SR here is steradian, which is the unit of a solid angle. I'll give you some time to solve this. This is also pretty direct, but yeah, I'll give you some time to solve this. Okay, I see one answer in the chat, B. I'll give 2 more minutes in case people are still solving and we can move to the answer. Please, others also put your answers. I only see one person in the chat. Okay, I see one more person says B. I'll give 2 more minutes in case more people are solving. Others, are you solving? Let me just check any other answers. Okay, I'll give 1 more minute in case someone is solving. Otherwise, we'll move to the answer. Okay, I'm going to move to the answer. I hope those of you, everyone has tried solving this. The answer is B. So well done to the people who solved it. So basically, what you need to do is find the solid angle. So if in case you don't know what a solid angle is, basically solid angle measured in steradians is the angle that is that is basic. It's more of, it's rather an area rather than an angle. Where you this basically this area is called a solid angle. So it is always defined with respect to the unit sphere, that is a sphere of radius 1, and whatever is the area of that segment that it subtends, that is called the solid angle. So basically this is how you measure the solid angle. And here you can see that this is essentially the setup that we have, right? We have a source and a detector, and we want to find what is a solid angle. So you, I know in the figure, because it's drawn in a like a one-dimensional, sorry, a two-dimensional way, you think that it just looks like an angle, but the solid angle is kind of, you can think of it as like a cone, and this is the sort of the solid angle, right? So the solid angle is not just a, just theta, it is actually two-dimensional in that sense. So here you have a cylindrical detector. So I guess this is, I took this picture from some other place, so that's why it's written like that. This is the source. So they have given you that R and D, and there's a way that you can basically link your solid angle and your plane angle, or the angle which you're used to. So if this angle is, for example, if this angle is theta, then what you do is you basically just find this area, right? And to find this area, you know how to do that. You just integrate over that polar coordinates of that. So that's we consider here a unit sphere. So whenever you want to, so R does not factor, and R is not changing anyway. So we have sine theta, d theta, d phi, and of course d phi so in case you don't know, this angle, right, on this plane is called phi, and this angle is called theta. Please look up spherical polar coordinates if this is not familiar to you. And essentially theta, you can see if this angle is theta, so the solid angle is basically that whole thing, but theta is like just the half angle of the cone. So if that is theta, that obviously the angle varies from 0 to theta, whereas phi goes around the full circle, right? So it's 0 to 2 pi. If you do the relevant integration, you will find that 2 pi into 1 minus cos theta gives you the solid angle. So now in order to find theta, we have to use this figure, and you can see that theta, if I drew theta here, I didn't mark it here, but if you imagine theta as the half angle here, then basically you can see that R by D gives you tan theta, and from that we can find the theta, and from theta we can then find omega, or the solid angle, through this expression. Okay, so here 2.54 has to be multiplied, because the dimensions were given in terms of inches, not centimeters, so that's why I have to multiply. So this is how you do this question. Is there any doubt in this question, or does everyone understand this? This is based on the definition of a solid angle, that's all. There's not, it's a mathematical question kind of, if you think about it. So this is the image that you need. This image is just to motivate what a solid angle is. Okay, so this is the actual image that corresponds to what was asked in the problem. I just wanted to, in case some of you don't know what solid angles are, I just wanted to put this quick derivation. That's why. And this is on Wikipedia, I think. So you can go and look it up later also. So I hope everyone understood this question. I will move to the next question. If you have any doubts, you can put it in the chat. If not, we can move to the next question. Okay. So mylar, which is this sort of polymer or whatever, is used as a target foil to understand the sorry, I kind of went to the answer. Sorry. Interaction of protons with carbon 12. And target of this much thickness is bombarded with 12 MeV photons in the experiment. So please calculate the number of carbon 12 nuclei present per centimeter square in the target foil. So this is the question. Please put your answers in the chat. And yeah, please, I see how quickly you answer the non problem, like how many people answer the problems which don't require solution, like calculation, versus how many people who answer the problems which require calculation. But please also calculate these things. In case you don't know how to solve, please listen to the solution and do try to do the solution and calculate it on your own later. And of course I can always make mistakes, as I said many times. So it's always good if you also solve and verify if the solutions are actually correct. So yeah, please put your answers in the chat. I'll give you a few minutes. Sorry. Okay, someone says others. I only see one person who has answered. Others also, I hope you're solving. Please answer in the chat. This is a counting problem, and we have done many such counting problems so far. So please, make sure you answer this. Okay. I see one more person says C. I'll give one more minute in case someone is still solving. Okay, one more person says C. I think we can go to the answer. So the answer is C. Again, this is a counting problem. You have to find the mass percentage of carbon in mylar. So, this is a compound which has 10, 8, and 4. So, 10 times 12 plus 8 times 1 times 4 times 16. So, if you find the percentage, it comes out to be 62.5. So, you know that if it's 62.5 percentage, then 4 into 62.5 percentage gives you 2.5. And then you simply do the regular Avogadro number scaling and dividing by the relevant molar mass, and then you will get the answer to be 10 power 20 times 1.254. So I think the person who answered D, you might have made some mistake in the powers. So just careful with that. But I think this is the correct answer. So yeah, please check it. It'll be like 23 minus 3 is 20 and you divide by 10. It's kind of like 112, right? This is 12, this is also 12, and this is 20. So that's how you get this answer. So please just recheck your answer in case you have made some mistake. Okay. So others also who have not answered, I think this is like, again, this is a counting problem. So be very careful with these things, finding number of moles from number of atoms, finding number of nuclei, atoms or nuclei, finding number of particles from the uh, mass. These are kind of simple things, and these are things where, if you know how to do it, it can really help you in your exam and generally also, because these are very general counting things which show up again and again in physics and chemistry. And I think these are things that you have been doing since you learned about moles in ninth standard or something. So this should be very easy to you. Okay. So yeah, that's about this question. Again, direct question. I don't have much to say. So yeah, here's another question. A proton with total energy 1.4 giga electron volt, GeV, which is 10 power 9 electron volts, transverses two scintillation counters which are 10 meters apart. So you have to find the time of flight. So I'll give you a couple of minutes to solve this. Okay, one person says B. Others, please answer in the chat. I see two people have responded. Others, please also, you also respond. Okay, one person. See three different answers right now. Any others? I only see 3 answers in the chat. I'll give you 1 more minute. We'll give 1 more minute. If anyone is still solving. Okay, one person says D. So I see that there is no majority answer. But yeah, the answer is actually B. I think the person has answered. So essentially here, what and all we were talking about, which was what I spoke about, special relativity plays a big role here. So you can see that proton has a rest mass of 0.938 giga electron volt. So you can find the gamma factor from that, right? So gamma tells you E by MP, which is 1.4 by, because E is just MP times gamma. So you can find the gamma factor. And from that, you can actually see what is beta. Beta is actually, in case some of you don't know, beta is called V by C essentially. And it's a very simple exercise to show that beta is 1 minus 1 by, 1 minus 1 by gamma squared whole root, and that comes to be 0.74. So 0.74 times C is your velocity. So essentially, you had to find what is the velocity, and from that, you can find what is the time. So comes out to be 45 nanoseconds. So you can see that it is quite relativistic in the sense that B is 74% the speed of light. The particle is moving at 74% the speed of light, but not really very relativistic. So when when the rest mass and gamma, when the energy is very much higher than the rest mass, it kind of tells you about how relativistic it is. So that is about this question. So if the energy is very much higher than the rest mass, it tells you it's moving at a very high velocity, which kind of lets you know how close it is to the speed of light. So that is the answer. Yeah, I think there is no confusion here. So let me just move to. So this is basically MC squared. MP here is written in giga electron volt, which tells you that there is already a C squared. Otherwise, it won't be written in giga electron volt, right? So as I showed before, E is not just MC squared, it's gamma MC squared. And sometimes people call gamma M as the relativistic mass, but we are going to keep it as gamma only, so that the mass remains an invariant. Okay, so that is kind of old fashioned. When you say that mass is increasing with speed, that's kind of an old fashioned concept. Nowadays, people just say E is equal to gamma MC squared. So that's why you have to find the gamma in this way. I hope this answers question when to use gamma and when not to. So that's the same as asking when to use relativity and when not to, right? So when you are very close to the speed of light, then relativistic expression becomes important, right? So if you imagine that suppose gamma is very high, right? Then you know that beta is very small, which means the particle is not moving at the speed of light at all. So, we don't have to, the those factors does not become important. But here we don't know that, speed is quite, it's quite high, right? It is 74% speed of light. So we, the only way to find that is by using gamma. So when can we use E is equal to half mv squared? When things are moving in non-relativistic speed. So that's why I spent the entire first hour of this lecture talking about special relativity and where it can be used and where it can't be used. So when gamma is very high, say gamma is above 100 or something, that tells you that beta is very small. It's not even close to speed of light. So we can go with E is equal to half mv squared. From which speed we should use gamma? There is no like cutoff or anything. I don't know. I think anything above like 60%, 70% speed of light is actually quite increased. And it also depends on the mass of the particle itself. So this is a very light particle. So you know that, it's moving at 1.4 giga electron volt. That means that this light particle is having a lot of energy. So that's how you know that the gamma is significant. That's how you know. So around 60%, I would say you can use. And particularly in these proton kind of experiments, you do need gamma factor. So you can calculate it and you can see whether it makes a difference or not. You can itself do an experiment in the sense that you can try with a few different gamma factors. You know all the expressions. I gave you a lot of the expressions, right? You can calculate for a particular value of gamma how much it deviates from the Newtonian expectation, and you can itself find out where it, and you can even write a small program for it if you want. So that's an expression you can do. So yeah, gamma has to be used when it is significant enough, and 74% is significant enough. So I think 60% is a good estimate. So here the same question as to what is the time of flight if the particle in the previous question is an electron. So here we solved it for a proton. The same question, but what if it's an electron is given here. Okay. I'll give you some time to solve this question as well. Okay, someone says D. Can you show the values? Yeah, sure. So this is the value. So here you have to solve the same question, but with electron. I can show you the options also. I don't see any answers in the chat yet. Anyone? Okay, I see one person says 33. 33. I'll give you one more minute in case someone is still solving. I'll give 1 more minute and then we'll go to the answer. Okay, I think we can go to the answer. Those who are solving, please check. So the answer is 33. So I think majority of you have answered that correct. So here you can see that electron has much higher energy than its, sorry, should be M. Yeah, so it's much higher than its rest mass. So we know that it's moving at some very high energy, which means it's basically close to the speed of light. So we can basically consider it to be moving at the speed of light. So again, the caveat that I said before, which is that massive particles cannot move at the speed of light, still applies. But because the electron is so light, it can approach very close to the speed of light. So you can try what we did for the proton case. You can try to calculate the gamma exact beta value, and you will find that it is very close to the speed of light, and you can find the exact time also. You will find that 33 is a very good approximation when we compare to that place. So I encourage you to do that exercise as well. So with that, we can move to the final question of today. So this is the question. In a beamline experiment to determine the cross section of a reaction, this is the target, this is the cross section. In the same reaction, when we use a target of a different thickness, what is the cross section that we can expect? So please put your answers in the chat for this question, the final question of today. Please put your answers in the chat. The final question for the day, we can wind up. Okay, I see one person says 60 millibarns. Okay, one person says 15. Okay, I see B and C as the options. I'll give 1 more minute in case someone is still answering. Okay, I think we can go to the answer. The answer is actually 30 millibarns. So the cross section is not affected. So can any one of you guess why this should be the case? Now that you know the answer, that the cross section doesn't change. So yeah, the cross section does not really depend on the thickness of the target, right? It depends on how many interactions are there between the target and the beam. And here the beam size does not really change. So what we expect is that the same, yeah, the same thick, so the same number of interactions should happen. And in that sense, we see that the cross section does not. Yeah, okay. So I think some of you are going along the same line, but yeah, essentially the interactions that happen are kind of the same. They don't depend on the thickness. So yeah, so that's the final question for today. So with that, we can wind up the session and all of the problem solving sessions for this. So I think we have covered a lot of different topics, both in this course and the problem solving sessions. And I've tried to make the problem solving sessions kind of have a little more extra material than what is just in the course, so that you can, if any of you find any of that interesting, that can be like a starting point where you can pick that up and go look at that more. But yeah, I hope that in general the problem solving sessions and the course have met your expectations. So as I said, this is the last official session, but we will be having one more session on. So once again, I'm reminding you that please mail me in my mail ID if you have something specific to cover. So I think someone already said cross sections like that. If you have some specific topics to cover, please include that as well. And yeah, we will. With that, we can end today's session. So thank you all for joining. And yeah, as usual, all the links are available on my website, and you can find the video and the slides. So please go back and like solve the questions if you haven't. And yeah, all the very best for your exam, and we'll meet again for the last time on Wednesday. Okay, so thanks everyone. I think we can end the session. So let me just, yeah, thanks guys. Bye.